All right, then maybe in terms of our next presenter, just Changfei confirming that you're in the virtual room as well.
Yes, I am here.
Awesome. So Changfei, if you can present from your side, that's probably easier than me turning pages for you.
Okay, I'm going to share my screen. Are you looking at my slides now, Mark?
Yeah, there you go. They just popped up in presentation mode.
Okay, great. I actually just came back from the classroom, so perfect.
Yeah, a special
timing.
thank you to Changfei, who literally, I think, ran from teaching his class to jumping on this call. So definitely appreciate the support. Thank you.
Thank you for the opportunity, Mark. And so I would like to take this opportunity to talk about our project and also share some of our experience, both in the proposal writing and also in the in the first year of the work. So our project title is Lab to Fab Transfer of CMOS+memristor chips for Edge Intelligence. They gave us a code name called Edge Intel, even though back then Intel was not in the best shape, but now it's getting better and better. I hope that's also the case for this project. So the background for this project is really we are trying to address the critical DoD needs for low power and low latency hardware for AI applications. Especially we know nowadays for the commercial AI hardware, represented by GPU from NVIDIA as getting more and more powerful. But on the other hand, those commercial hardware, they do not necessarily address the unique DoD needs, especially in the size, weight, power, and aspects. And if we want to have deployed or the intelligence to the edge for DoD applications, either it for, let's say, a drone fly outside or to the soldier in the battlefield or for the battleship, either above or below the surface of the water, we need intelligence devices that, number one, is power efficient. So most of the cases we are running in a power constrained environment. And number two is it can make decisions on the edge, meaning we do not have to send the data back to the cloud to make decisions, because more than often it's going to be too late. And of course, that also means the size got to be small, the weight to be low. The emerging technologies beyond CMOS and is actually we believe it's going to offer an alternative solution, especially those combine the benefits of the emerging devices and also the mature infrastructure of the CMOS industry, or in other words, we should take advantage of the CMOS plus X platform. So we have been working in this domain for over 16 years in the university research level. We worked on a device. It's called memristor. It's actually analog memristor. It's not just simply memristor. It's a two-terminal device with a switching layer sandwiched between two electrodes. The conductivity, the conductance or resistance of this layer can be modulated by the electrical field applied across these two electrodes. As a result, we are able to use the multi-level conductance or resistance to represent analog or digital information. So we have engineered a device that meets most of the requirements for in-memory computing architecture for the artificial neural network. We moved one step further. We integrate them into large-scale arrays. For example, in the middle of this picture shows here is a different number of the one transistor, one memristor arrays. With these arrays, we demonstrated a lot of very interesting machine intelligence applications, from the very simple two-layer perceptron for object classification, or we can use it to do the gate classification by partitioning them into fully connected layer, and long short-term memory, etc., etc. We also, in collaboration with our computer scientist, Andy Bartle, who actually just won a Turing Award this past March for his reinforcement learning. We demonstrated back in 2019, we can use this hardware to demonstrate some primitive reinforcement learning mechanism. By the way, reinforcement learning is one of the two major algorithms for AlphaGo. It's also one of the major algorithms used for the ChatGPT nowadays. We further build them into 3D to do the one-shot convolution. So on the left side of this panel, of this slide, is all the university research we and our collaborators have demonstrated. That's actually built a very strong foundation to a stage that we decided we probably need to, it's right time to take this to industry. So we start a small startup. It's called Tetramem. And in the startup, we keep doing the device optimization. For example, we can program the device to over 2,000 conductance levels, or in digital words, that equivalent to 11 bits. And more importantly, we integrate them into the CMOS circuitry, a 300 millimeter wafer scale, and then package them into the evaluation kit. So first generation was 65 nanometer CMOS, and then the evaluation kit is right over here. It's called MX100. With this evaluation kit, we demonstrated another whole set of applications. A lot of them are actually very relevant to DoD applications. For example, we use this for RF signal processing. I mean, in addition to the previous demonstrated neural network applications, we expanded the application to signal processing, especially in the RF domain. Number two, we also use this for the scientific computing. For example, what we are showing here is the Navier-Stokes equation. It's a partial differential equation solver. This is also inspired from application DARPA really wants. If you want to calculate the turbulence flow in the plasma, that's actually what the project was about. So, so those are the prior work, and I'll say that leads to the hub project. But on the other hand, we need to understand the landscape of the entire technology worldwide. So we did a study over here for this memristor or ARM technologies. There are basically three different kind of business models. Number one is you use it to build microcontroller and to make the standalone product, especially the microcontrollers for the automobile industry. So most of the companies over here, they work in this domain, but of course the device, they work still in binary ARM, or you use the license, right? You license technology into the foundries or other companies. For example, there are a few companies in Australia, in UK, and Israel. Again, mostly they use binary devices. And the third category is you use this device for the AI machine learning accelerators, because intrinsically, if we can take advantage of the laws of physics, you're using the Ohm's law for multiplication and using Kirchhoff's current law for summation, you can do the vector matrix multiplication in one shot. That's a very, very attractive application. Think about this for ChatGPT, and 92% of the resource that's actually measured by SK Hynix in 2023. They published that data in 2023. 92% of the resource in ChatGPT training is used for the vector matrix multiplication. So unfortunately, if you look at the landscape in this domain, most of the companies actually overseas, and Tetramem is the only one that's actually doing the AI accelerator SoC within US, and our differentiator is really the analog memristor over here compared with most others who are working on the binary devices. So let's go back to this project. This project is really focusing on the lab to fab transfer, and is also moving from to the advanced CMOS node. For example, the evaluation kit MX100 we just showed over there is based on the 65 nanometer CMOS node, and the integration is on top of metal 6. That's the topmost metal layer, which has a pitch 800 nanometers is huge, right? And certainly with that, you can make some, but you're not going to make a whole lot of devices, right? And then for this project, we use 12 nanometer. So we advance from 65 directly to 12 nanometer. Furthermore, we move from the topmost level metal all the way down to metal 1. Again, for the 65 nanometer CMOS, there's only 6 metal layers. For the 12 nanometer LP plus, it's 11 metal layers. The reason for that is it's actually very straightforward. For the pitch we just mentioned for 65 nanometer, the top metal pitch is 800 nanometer. For the metal 1 of 12 nanometer, that can be as small as, I believe, 64 nanometer. So you are looking at a potentially 160 times density boost. So that's very, very attractive. Of course, the benefit of moving to smaller node involves, we need peripheral circuits. The smaller node CMOS transistors are going to give us much, much better power efficiency. Of course, this is also going to give us a lot of challenges. Number one is the device geometry is going to change. The thermal budget the device stack is going to experience, it's going to be very different. Think about you put your device layer right over here and you build metal layer all the way up. The thermal budget is very different from the 65. And of course, they're also important is we want to make sure this technology by the end of this project is going to be available in a mainstream IC foundry that is on US soil. That's critical for this ME Commons project. So with all this goals in mind, we formed a team which consists of different sectors. We have academia such as UMass Amherst, University of Southern California, et cetera. And we also have startups such as Tetramem. And then we have the R&D facilities such as New York Craze, which is a great segue into a mainstream IC foundry, which is in the backyard of New York Craze, that's Global Foundries. And we also have the defense contractors who is going to validate the hardware at the end of the year 3. So on the right, you can see what the different organizations are going to do. So the university is still going to do the device and process optimization. We understand to transfer a device and the process from the research lab and a small startup into a mainstream foundry. There's still going to be a lot of change, which actually I'm going to talk about later in more detail. And then the startup is going to develop the IC design, the system design, and also equally important is the SDK, the software stack development. And then the Global Foundry and New York Craze, they are doing the PDK development and chip prototyping. So they have established a split fab protocol, which we are taking advantage of. And on top of this, the system validation is going to be done by Raytheon and BAE. So that's also taking advantage of the entire ecosystem in the Northeast region of the United States. So that's about this team. Now we are into 1 year of this project. I think we are very happy to announce that we have delivered both of the go/no-go metrics. In the first year, the first CMOS design was taped out and fabricated in the commercial foundry, which is Global Foundry. On the left is our layout, and in the middle is actually a intentionally blurred image. It's 12-inch wafer. The reason Global Foundry wants it to be blurred is because it's not just only our circuits here. It's multi-project wafer. So there's a lot of other people's circuits over here, and then they want to make sure with our eagle eyes we do not see other people's IP. But this is the exact wafer we are dealing with. Our circuit is a tiny little part right over here, I believe. And then we also working together with both New York Craze and Global Foundries. We have developed the back end of the line integration process that is going to be acceptable by Global Foundries. There is also device development, especially the memristor or ARM module development and optimization. So on the upper right, you can see that's the memristor array integrated with this 12 nanometer CMOS wafer. And then on the lower right, what you're seeing here is the memristor module we developed over here. And we can tune the large array level, and each of the cell can be tuned to 196 levels. That's limited by the ADC design. That's 7.6 bits, equivalent bits. Actually, our goal is really 8, but the ADC was only achieved the 7.6 for the moment. So, but I mean, this certainly shows the device once moved out of the research lab, going to the fab, we can still get into that level of tunability. So that's the kind of a status for the year 1. As we just mentioned, in year 1, we are happy we met both the go no go metric. One is tape out, that's over here. The second is the the integration, and we also started on working on the year 2. So year 1 is the tape out only has the array. There's no proof of circuits. So in this array, we have 4K by 1K, total 4 million bits, 1T1R bits. So the transistor used as a pass transistor, and the memristor is connected into each of them. So this is really a kind of a pipe cleaner, try to make sure the device stack, the integration process is going through the R&D facility with its newer craze, and then be accepted by the global foundries. And then in year 2, we're going to do the second multi-project wafer. We're going to tape out what we call the MPU tile or MPU slice. In this case, we're going to have the on-chip analog driving circuits and sensing circuitry. So in this case, once we have the chip out and package it, we are able to program those arrays or part of them through the on-chip circuitry. So that's the goal for year 2. I think we are right now in the process of designing those MPU tiles, and we are in I would say we are on track with progress. So once the year 3, which we are not showing here, is once year 1 and year 2 are successful, we're going to tape out a full MPU macro, which has the full 4K by 1K, 1T1R crossbar arrays, all the proof of circuits, and so we can package them and then demonstrate the functionalities. Especially, we're going to be working very closely with RTX, in particular Raytheon, and to work on some of the either some of the data or some of the problems they're really eager to solve. So, if, for example, we have the need for the low swap from the RTX and BAE systems aligned very well with our vision. So we are going to be, by the end of year 3, we're going to be providing them with packaged chip, and then they can play with the data on their own facility. On the commercial side, we're also very excited. We're working with Tetramem and its customers, trying to bring this into the commercial market, especially for applications that requires low power, low latency, and that need to make decision at edge. So there is certainly a lot of interest in this domain for this technology. Once it's successfully transferred to a mainstream foundry, we envision this is going to have a dual, capability, both for the DoD and also for the civilian applications. So that's the all we have for the project we have. And now I'm going to switch gear to what it takes us to go from the beginning of the, let's say, ideal conception to the year 1. So this is a timeline about this project. Actually, I started with the August 2022, when the CHIPS Act was signed into law. Immediate after that, you see there is the Microelectronics Commons was launched. It was based on the $2 billion going to DoD is the government established the Microelectronic Commons. The main mission for the ME Commons, as James just mentioned, is really trying to address this the valley of death, right? There's a lot of great technology in this country, in the universities, in small companies, but there's no mainstream foundry that would like to take it. So that's the mission for the ME Commons. And then the request for solutions was requested. And since then, even though we did not call ourselves the NEMC Hub, there were a lot of activities going on. Say, for example, I still remember Mark Goker from Lincoln Lab organized a lot of workshops, right? We also collected exemplar projects and abstracts, et cetera, et cetera. There were a lot of presentations and ideas floating around. And then based on all these presentations, and then there are few projects were chosen, and then was part of the package into the hub proposal. That was February 2023. And then in September 2023, the hub award was announced, and NEMC is one of the 8 hubs won award out of the 83. I believe the number was 83 competitors. And then a few months later, the call for project released. So in that call for project, there are a number of topics. I believe total was like 47-ish topics. Those topics were chosen from the exemplar projects we submitted. And then starting from the January 2024, the hub solicited summaries. In basically the hub solicited summaries from everybody. Okay, write the project you want to propose if you believe your vision aligned with the call for projects. There's only 1 month for that, because the full proposal is due February 28th. So there's only a month. So there was a summary chosen in February as a month for the proposal, and everything was starting from there. About 4 months later, we started receiving the question and answers from the government. This is a very different evaluation process. It's actually the government is doing the same thing this year for year 2 renewal. And they ask questions which we need to address, and which will also need to incorporate into the technical volume. And then they only give us probably a couple of weeks, and then we send that back. And in 3 months later, the project award was announced, and the number was September 17th. And then in the NEMC hub, and together with a couple of other hubs, the announcement was made in the Lincoln Lab in a tent outside. So that's the timeline for this. I think it's probably going to be similar, and for this round, except that we're probably going to start with the call for project release very soon. So we're going to start from here, and the rest is likely going to be similar. But of course, the government keeps changing rules. So from the project, perspective, we do have some changes. For example, originally we proposed we're going to do 22 nanometer FDX process with the and integrate our analog memristor between metal 3 and metal 4. And we realized when we talked to global foundries, that was not aligned with their interests. So we actually changed the technology node from 22 to 12 directly, and that aligned better with their interest. And actually, after all this careful evaluation, we figured that's also better in terms of the transistor operation. We need certain voltage and current to operate our device. The 12 nanometer LP path process with the hybrid transistor actually works better. Number 2 is we have to change the device structure and also change the device stack. The reason for this structure change is, for the MX100, we integrated on the very top layer, metal layer, and the device structure we call it the VIO structure. And then that's avoid some typical problem in the industry. But when we talk with global foundries, they came back and said, well, you need 2 extra masks for that device structure, even though the whole stack is 62 masks. They said we cannot afford 2 extra mask layers. So you got to change that. So we have to do that. And we changed the device structure into H-based structure. That's actually created a lot of challenge in the past few months. That's why we have to add it in the deliverables. We added short loops, and there's a lot more characterization, a lot more electrical testing, et cetera, et cetera. Some of them actually are still ongoing, but I'm very happy that with the close collaboration with Global Foundries, New York Craze, and Tetramem, and the entire team, we actually keep moving and keep making progress, even though there are changes in the technical aspects. So finally, I want to share some of my personal take on this project. I call this reflection points. A very important point is, especially this is for our academia friends, this research project is very different from, I call it regular research project. Regular for us is, say, for example, we write a proposal in NSF and they give us the money, and then we spend it and write paper, publish it. That's usually the case. But actually, for this project, it's different. As we just mentioned, the mission for ME Commons is really trying to address the value of this. We want to make sure this is a technology that is going to industry. So the ultimate deliverable is not going to be papers. It's not that important, number one. Number two, we do not have that much time to do the try and error. And if we have a different splits, we do not have that luxury. Like in our lab, we go down the lab and tomorrow we'll find a different table. No, because we are also working with real industry. Industry that main deliverable is to make the profitable like product, right? So we will have to coordinate very well. And so that's number one. So this is really very, very different type of project. It's very, very transnational. Number two is always good to start as early as possible. There's a couple of reasons. Number one is we are relying on the multi-project wafer process. Those shuttles is like train, right? Once they have the time to go, they leave without you if you do not catch it. So you're going to be delayed by a few months if you do not catch the designated shuttle. Number two is there are unexpected things that could happen. For example, we had to change the process, right? We had to change the technology node. So those all happen. We should allow time for that. As a matter of fact, for our project, the design part started even before the designated shuttle time, because we realized if we do not start it back then, we are very likely to miss the first shuttle. We did not want that happen. So number three is very important is we should keep our promise. We should deliver the milestones on time. So the government checks it, the hub help us check it. The ultimate goal is really want to make sure Rome is not built in one day, right? All the small milestones that are going to accumulate into your final goal. And of course, Rome is not built by one person, so there's an entire team. So we should keep the communication channel open all the time. The communication between your team members, that's all the people working on this project, and then the communication between the hub, and that's extremely helpful. Especially, Mark and Emily has been working on our project a lot, and Mark has personally, he's a veteran of startup, if I'm not mistaken, and his past experience is very helpful. And Emily herself spent many years in a real foundry in North Andover, so that's also a very helpful experience for us. Of course, the government, we need to keep the communication channel open as well, because we need to keep updating them what's going on, and we also need to let them know what we are trying to deliver, because there are a lot of people come and people go from the early days to now. So that's we need to make sure we need to have communication open. And finally, I think it's also very important that when there's meeting, if we can make it in person, and I believe James agree on this as well. And it's actually way more. I understand there's a lot of technology nowadays. We can keep all these meetings virtually. But say, for example, I personally travel to Albany a lot. So that's every time I meet engineers and I meet the technical folks over there, it really makes some difference. It really makes the difference in addressing all this all this technical and also logistical challenges. I believe I'm over time as well. I'm going to stop right over here, and I'll be happy to answer any questions you have any. Back to you, Mark.